Hello, this is Kyle Akridge and Jordan Richardson's final project for AI on job scheduling. So first up, we have understanding NP-complete problems. NP-complete problems are a class of problems in computational theory that can be NP and NP-hard. So first up, we have polynomial time, and its definition is problems that can be solved quickly in polynomial time by deterministic algorithms. Then we have NP, which is non-deterministic polynomial time, and its definitions are problems for which a solution can be verified quickly in polynomial time, but may not be quickly solvable. And then last up, we have NP-hard, which its definition is a problem is NP-hard if an algorithm for solving it can be translated into one for solving any NP problem. So characteristics and relevance of NP-complete problems. The key features of these problems revolve around the fact that they are solvable and verifiable in polynomial time by a non-deterministic machine. However, no known algorithm can solve these problems quickly on a deterministic machine. Deterministic means that given a particular input and state, it will always produce the same output and transition to the next same state. These problems are important because many real-world problems in different fields are NP-complete, making the study of these problems crucial for developing efficient algorithms. So here we have the job scheduling NP-complete problem that we focused on this project. This study focused on the job scheduling NP-complete problem, which in real-world production and computing is crucial to efficiently organizing tasks for optimizing time and resources. And then here we have three of the components involved. So we have jobs, and then we have machines, and then we have completion time and processing time. Job scheduling problems involve scheduling a series of jobs, each consisting of a sequence of tasks to be processed on different machines, while each task has its own completion time and cannot be reorganized. The objective is to minimize the total time taken to complete all jobs and tasks. So why is job scheduling NP-complete? First, we have complexity. The complexity of job scheduling increases significantly as the number of jobs grow. This is because each additional job adds a new layer of possible permutations for the order in which jobs can be processed. The number of possible variations in job sequence grows factorial with the number of jobs, which means the problem's solution space expands rapidly, making it computationally extensive to find the optimal sequence. Then we have scale. As the number of machines increases along with the number of jobs, the dimensionality of the problem also increases. The scaling issue means that the computational resources required to solve the problem can quickly become prohibitive. The complexity of finding the optimal solution in a job scheduling problem is factorial, not exponential, which is far more daunting as factorial is a lot bigger of a number than an exponential. So for real-world implications, in real-world manufacturing and production settings, job scheduling complexity can lead to significant bottlenecks. The ability to effectively schedule jobs has a direct impact on the efficiency of the entire operation. Then we have order preservation. Maintaining the correct sequence of operations is crucial because in real-world manufacturing processes, most tasks have to be completed before others can begin due to technical or logical dependencies. So for optimization versus exact solutions, in the realm of NP-complete problems, it is often unfeasible to find an exact solution within a reasonable time frame, especially as the size of the problem increases. This leads to a reliance on approximation, optimization, and heuristic methods to find the solutions that are good enough within the constraints of time and computational resources.
Below is a data set of 10 jobs, each with 10 machines that have a completion time. Because we cannot reorganize the machine order, we must reorganize the job order so time can be cut shorter. The way this happens is through ensuring that machines finish accurately to move on to the next task. It is critical in various fields, including manufacturing, computer task scheduling, because efficiency directly impacts productivity and cost. So here we have 10 jobs with 10 machines and completion times per jobs, which are the pairs, which makes it become a 10 by 20 array. So let's give you an example of how this works. Before sorting, this schedule of jobs has 3,802 seconds to completion, about 380 seconds per individual job. After sorting, it takes about 3,549 seconds on average. While this time completion may not make a large difference in the short term, however, in a factory where tasks are repeated daily hundreds of times, it can make a huge difference in the productivity of a business and its success. Given that after sorting, we save around 253 seconds for each job cycle, The company repeats these job sets around 22.7 times a day, given 3,802 seconds, which is about 1.05 hours per schedule. We can then do math on that, and that means they can complete around 82,855 individual jobs per year. The company utilizing job scheduling repeats these job sets around 24.3 times a day due to it only taking 0.98 hours per schedule. We can then do math on that to figure out they can complete 88,695 individual jobs a year. This is a difference of 5,840 individual job completions, which can potentially be a huge profit increase many companies will be missing out on if they complete jobs without utilizing job scheduling. The GA starts with the given number of generations, population size, crossover rate, mutation rate, and the tournament size given by the user. The GA functions by first creating an initial population of X schedules of jobs that are randomly created from the initial schedule that is being optimized. It then calculates the fitness of all schedules created from the population and documents the best schedules for the generation based on the minimum time to complete the jobs. A new population is then created based on the best individuals identified from their fitness, which is known as elitism. Then tournament selection is used to select parents for the reproduction of the new population. Crossover is performed between two parents, essentially combining them into one. A mutation is also sometimes performed, which makes small changes to the offspring produced from elitism and crossover. This helps to introduce more diversity into the population. Population is then finished off by adding the offspring from the above steps and the initial elite schedules obtained. It continues until a termination condition is reached, which in this case is the number of generations initially specified by the user. This is our approach to job scheduling on our individual functions. First, we have the initial population. The initial population is generated by creating multiple random job schedules from the data file. Everyone in the population is a list of jobs, and each job is represented as a list of tuples. Each tuple contains a machine and the time required for that machine to complete its part of the job. The function randomly shuffles the order of jobs for everyone in the population. This ensures a diverse set of starting solutions. Swap mutation. The mutation process introduces variation into the population. It randomly selects a pair of jobs with an individual and swaps them. The number of swaps is determined randomly, up to half the length of the job list. This randomness and mutation helps to explore a wide range of solutions and prevents the algorithm from being stuck in local maximal. Tournament selection is a method of selecting individuals from the population for breeding. The tournament selection function randomly selects a group of individuals from the population and then chooses the fittest individuals among them. The size of the group is determined by the tournament size, which is decided by the user. This method balances between selecting the best individuals for breeding and maintaining diversity in the population. Crossover. The crossover process combines parts of two parent individuals to create new offspring. It does this by iterating over pairs of genes, in this case jobs, from both parents. If a job from the first parent hasn't been added to the child yet, it's added. If it has, the function tries to add the corresponding job from the second parent. This process continues until the child has a complete set of jobs, which means that the offspring inherit characteristics from both parents, promoting the combination of successful traits. Lastly, we have wisdom of crowds. Wisdom of crowds is a concept that involves creating a solution based on the best performing schedules in your population. Here's how we implemented it. The store top solution function identifies the top performing solutions based on their fitness. This subset represents the best solutions found by the genetic algorithm so far. The create WOC solution function generates a new solution based on the most common job sequences and the best solutions. It counts how often each job appears in each position across all top solutions. It then builds the WOC solution by selecting the most common job for each position. The selection is based on the frequency of appearance and ensuring that jobs are not duplicated. If any jobs are missing in the construction and solution, they are added to the WOC solution. This process effectively creates a new solution that represents the wisdom of the best solution, assuming that the most common choice among the best solutions are likely to lead to a good overall solution.
So now how did our WOC perform? WOC does have a massive impact on the outcome of the GA, given the right conditions. So we have three sets here. We have a 10 by 10, 20 jobs by 15 machines, and then we have a 30 by 30. So we can see here for the 10 by 10, the WOC was better 4 out of 10 times. For the 20 by 15, the WOC was better 5 out of 10 times. And then for the 30 by 30, the WOC was better 7 out of 10 times. So from our iterations, we found that as complexity increases, WOC outputs better results. And we believe that this is due to the increase in variability. However, it is also important to realize that while these iterations were very quick, in real-life applications of job scheduling, execution time will increase drastically. So WOC can make a huge impact on finding a minimally viable solution. So here we have the wisdom of crowds effect on a 100 by 100 data set. So while wisdom of crowds does not always perform well on smaller data sets, this problem inherently would have larger data sets due to its ability to apply to real-world situations in manufacturing and workspaces. As you can see, WOC created a solution around 55,000 seconds faster, 5,500 seconds faster than the regular GA. This was also completed in its entirety in under 5 minutes, which means that a viable solution can be easily retrieved for a workspace in a very timely manner. And then we can see the graph on the right. So here we have a results table where we varied some of the input variables such as population size, generations, elite count, tournament selection size, and then also the number of runs that the GA ran before the WOC combined their results. So if we look at the first column, the WOC outperformed all of the GA runs, and then also in the last column, the WOC outperformed all of the GA runs. So how does our algorithm minimize make span? So the make span is the total time required to complete all jobs or the schedule of jobs. While the machine sequence cannot be changed for each job in the job sequence, the order of the jobs can be changed. The reason that this speeds up the make span to complete all the jobs is because of machines being freed up, possibly based on a different order. Since the jobs can all run at the same time in theory, the optimal combination will be the sequence of jobs in which the time that machines are waiting to complete the previous task is minimized. Essentially, the order of jobs affects how and when machines become available for subsequent tasks. Doing the WOCGA algorithm creates subschedules of the original schedule moving around the ordering of the jobs, and determining how long it will take to complete the entire schedule of jobs. Doing this over tens to hundreds of generations, keeping the optimal schedule each time, helps us to find an optimal schedule that decreases the minimum make span and ensures that jobs are not held up by machine bottlenecking. So in conclusion, I think that JSP and TSP share many similar attributes such as optimization, the uniqueness of the problem, and the complexity of both. This project allowed us to explore into genetic algorithms and the wisdom of crowds approach on a new problem. The whole semester when we worked on TSP, it was very insightful to use this new algorithm, or to use the algorithms that we focused on for the semester on a new NP complete problem. There are more algorithms and more ways that we could scale to higher complexity for the JSP, but even to be able to handle 200 jobs by 10 machines and still retrieve fair answers is pretty miraculous considering that it would take 200 factorial permutations to find the 100% optimal solution by brute force, which is 7.89 followed by 374 zeros. And so that is the end of our PowerPoint presentation. So now we're going to jump into our demo. So first we're going to run the job generator, which creates our unique set of jobs each time. This is what we used. This is basically what we use for all of our testing. So we can create just a simple one here, 15 jobs, and we'll go up to 4 machines, and we'll just keep it with the default instance name that we have. And then after this runs for about a second or so, we get where we can actually change all of our variables such as mutation rate, crossover rate, population size, generations, elitism count, tournament size, and then the number of runs for the GA. So we can bring down the generations just a little bit. We'll bring it down to about 25, and then we'll keep everything else the same. And then we can select our file of our generated instance that we just created, and then we can run on it. And we can see it running down there in the bottom. And then as soon as it finishes, we get a nice graph up here, and we can go through the run. So this is one GA run, and then we did 5 total runs. So this is the 5th GA run. And then, so this point here is the last iteration of the GA, and this down here is our WOC point. So we can see that our WOC did run approximately roughly 200 seconds better than our best GA run. Thank you.